try this again. So, slideshow from current slide. All right, let's talk naming, kids. These are all sorts of names that could have happened if chemists were involved. Not necessarily, but we like to think so. All right, there's two types of compounds. There's ionic, which is between a metal and a nonmetal, and there's covalent between two nonmetals. Covalent is more of a sharing. Ionic is more of a hostile takeover. More on that later. Don't get me started. Okay, binary elements, binary ionic elements, binary ionic compounds are made of two elements, a metal and a nonmetal. So sodium and chloride, or barium and bromide. So even though there's three atoms here, one calcium and two bromos, we still say it's binary because only two elements are involved. There's also polyatomic ionic, in which case more than two elements are involved. So here calcium, carbon, and oxygen are all involved, or sodium, oxygen, and hydrogen. So these are polyatomic, these are binary. We will also talk about covalent compounds, mainly organic CH bonds, later in this unit, but about 95% of what we're talking about is right here. Let's get started. So binary ionic compounds are going to do this Leo-Gur thing. Leo-Gur is a wonderful way to remember that if you lose electrons, you're oxidized. That would be the lion's name, Leo. Those of you who look at your astrology symbols. I think that's it. Anyway, if you gain electrons, you're reduced. So the lion says Gur. This lion's a little more adamant. That's more of a roar. But anyway, you get the point. Gur. Gain electrons, reduce, lose electrons, oxidized. So what does that mean? Well, it turns out that certain elements on the periodic table always do certain things. The first row always lose one electron to become +1 ions. The second column here always lose 2 electrons to become +2 ions. Silver always loses 1, zinc always loses 2, aluminum always loses 3. These are things that always happen, never fails. On the negative side, everything here, which is almost a noble gas, fluorine, chlorine, bromine, iodine, whatever that is, gain 1 electron to become like a noble gas. Things here gain 2, things here gain 3. So if we're looking at, say, sodium wants to become like a noble gas, like neon, and it does that by losing, oops, that's not what I want to do, let's do that, by losing 1 electron and becoming like neon. Magnesium, no, I bet you I do calcium. Calcium in row 2 and anything else in row 2 will want to lose 2 electrons, one to get to the first column and the second one to get to argon. So in the process of losing these, they are getting oxidized. They're becoming more positive. Electrons are negative. So by losing 1, these all become +1. And by losing 2 steps, these all become +2, the beryllium, magnesium, calciums. All right. On this side of things, they're so close to noble gases, they don't want to lose, they want to gain. So the first row, the halogens, the group 7A, are so close, they're just 1 step away. The second column away from noble gases are 2 steps away, so they get a charge of -2, and this third group here are just 3 steps away, so they pick up 3 electrons to have a charge of -3. So -1 for all of these, because they just need to take the 1 step to become a noble gas. -2 for the oxygen group, because they need 2 steps to become a noble gas. And -3 for the nitrogen group, because they need 3 steps to become a noble gas. In the process of gaining these electrons, they're becoming negative. They're gaining electrons, they're being reduced, they become negative. All right, I'm happier with that. So far, so good. So at the end of the day, group 1 is always +1, group 2 is always +2, aluminum is always +3, zinc is always +2, silver is always +1. Right? 1, 2, 3. These 3 in diagonal. All right, the transition metals are wild. We'll get into that in a second. Halogens are always -1, oxygen group always -2, nitrogen group always -3. Let's talk about the transition metals being wild. So everything that's not colored in here is not colored in because it doesn't do anything consistently. And since it doesn't do anything consistently, we say they're wild, right? Except for the zinc and silver. These all can do multiple things, and you don't know what that multiple thing is until it tells you. And how is it going to tell you? Well, it's going to tell you with a, oh no, I forgot it again. Hold on a second. Pretend that did not happen. All right. It's going to tell you because of, hold on a second. There we go. Nope. All right, that was horribly choreographed. So now you know. That's, I did a dance when I was in my senior play. When I was a kid, they used to have seniors can't get cut from the last play of the season. I didn't get cut, but I got pushed to the back. We did Grease. All right. So choreography, not my thing. But the point being, all these white things here, you don't know what their charge is unless a Roman tells you. And that Roman numeral will tell you what the charge is. So let's talk about what we need to do. So to determine the charges of each element involved, so barium is here, so you know it's +2, and chlorine is here, so you know it's -1. So barium and chlorine are getting together. The barium's going to be +2, the chlorine's going to be -1. Match like we did with the puzzle pieces, and the name will be the metal, barium, plus the non-metal, chlor, with an "ide" ending. So chlorine with an "ide" ending is chloride. So that would make barium chloride. And puzzle piece wise, oh boy, just a glutton. All right, puzzle piece wise, it's going to look like this. So here's the puzzle piece for barium. And that has 2 positives, right? 2 positives. There's 1 and there's 2. All right, chlorine has minus charges, so let's make it a different color. So here comes chlorine with its minus. And as you can see, with just 1 minus, chlorine cannot undo. Wait, can I undo that? Undo? Oh, no. Maybe I can erase it, though. Erase? Oh, yes. There we go. That. All right. Well, there's a C, and there's an L. Look at that. All right. So 1 chlorine isn't enough because this other positive charge is still here. So you need 2 chlorines, 2 abnormally large chlorines, 2 chlorines that are undergoing severe chromosomal growth issues. So 2 chlorines are needed to go with 1 barium. So you have barium chloride. Let's try it here. So potassium chloride. Potassium, has a +1 charge because it's in group 1. Chlorine has that -1. So the puzzle pieces would fit in like that, where this is potassium, this is the chlorine. Let's see if I can do that a little better, right? That's the chlorine, and the other one is the potassium. And the other one is the potassium. So they need just a 1-to-1 ratio to tie each other up pretty well. And that makes potassium chloride. All right, so magnesium and chloride. Magnesium is in group 2, so it has a +2 charge. Chlorine has the -1, so the +2 charge is going to look like this now. It's going to have 2 places, 2 pluses, 2 pluses, and the chlorine is going to have a -1 charge. So it will take 2 chlorines to equal out what the magnesium brings, and that makes the formula MgCl2, magnesium chloride, 1 positive and 2 negative. Let's do our own example. So sodium, if you look, is a +1 and a plus. And oxygen, if you look, is a -2. So what that means is that oxygen has 2 minuses on it, and the sodium has its 1 plus, right? So therefore, in order for sodium and oxygen to be nice and neutral, there will be the need of 2 sodium atoms. 1 isn't going to do it because this one down here is still open. So let's go for a second one. And there you go, sodium plus. All right, so this Na2O is what sodium and oxygen would be. And it's sodium oxide, Na2O. So aluminum, you may remember, is one of those that has 3 always. It's the only one that always has 3 positive. So aluminum is always 3 plus. And nitrogen, if you consult your periodic table, is 3 negative jumps away. So nitrogen is going to look similar to Indiana and have 3 negatives. So you just need a 1-to-1 ratio of these for everything to be tied up. So that's aluminum and aluminum nitride. This is awful. All right, but hopefully you get the point. So, oh, I had that there so I could, anyway. Let's talk about Roman numerals. So Roman numerals are telling you, so if it's not group 1, group 2, silver, zinc, or aluminum, you don't know what the charge is because it changes. So we have to tell you the charge using a Roman numeral. Here are the Roman numerals in case you didn't know. There's lines for the first 3, then you start doing IV for 4, V is 5, so IV is like 1 before 5, 5, and then 1 after 5 is 6, 2 after 5 is 7. So these Roman numerals are telling you the charge, folks. They're telling you the charge, not the number of things in it, right? All right, that's going to cost me. So you have to still balance your charges and everything. So tin 2 chloride, this is telling you that tin's charge is +2. So SN, if you're keeping track at home, has a +2 charge. Let's make it like that. That's awful. Anyway, so chloride has a -1 charge. I'm going to change colors anyway. I mean, this is already abysmal. So it started off good, and then it just went downhill. So here's 1 chloride, right? And that's not enough. So you need 2 chlorides to make this happen. That's not my worst job, right? You need 2 of these to balance out those 2 pluses. So tin 2 chloride is SnCl2. All right, so lead oxide, there are 2 oxygens. Each one has a -2. So, oh my gosh. All right, that'll work. So here's 1 oxygen with a -2. And here's a second oxygen with a -2. So those are 2 oxygens with -2. So the lead, there's only 1 lead. And how is 1 lead going to do this? Well, it's going to do it by making the shape of New York and having 4 positive charges to counteract each of those negatives. So what we learned here is that I have absolutely no fine motor control, and that lead is +4 rather. So that would make it lead 4 oxide. That's how you would call that, lead 4 oxide. Get me out of here. All right, so charge is doing that. All right, now another way to do this is this crossing thing. I dislike this, but if it's, midnight and the test is tomorrow, this does work. So you just put the charges down for each thing involved, and then you crisscross them so that the charge for magnesium becomes the number of atoms of chlorine you need, and the charge for chlorine becomes the number of atoms for magnesium you need. This has a lot of issues. Since 1 is understood, since you went through all the trouble to draw out Mg, therefore magnesium is 1 and chlorine's 2. The other thing you have to remember is to reduce to the lowest number. So if this was 2 and 4, you would have to go down to 1 and 2. If it were something like anyway, you have to reduce to the lowest number. That's all. We're going to start polyatomic ions on another video. I am done with this. I think that's better. Others may disagree, but that's all right.